Hi there, it's Z here, and welcome to the third video in a series of videos related to using the tools of linear programming to help support the capital budgeting decision problem. If you've just joined us in this video, you may want to try and go back to the first two videos to get uh, a better idea of what we're trying to do. But otherwise, I'm just going to dive into it. So where we last left off, we were at scenario 2, and I'm going to talk about scenario 3 here. Scenario 3 is similar to scenario 2, but you start to get more complex constraints that are a bit more reflective of what you expect to see in the real world. So uh, just like before, we have multiple years where there are constraints in capital for each individual year. But in addition to that particular constraint, you now have a case where two projects uh, must happen at the same time or not at all. So essentially, this is an artificial example, but you could say that maybe it's because they're both in the same facility. It doesn't make sense to only do one and not the other. So if one happens, the other one has to happen. But at the same time, you have uh, another scenario where these two projects, um, again, contrived example, but let's just say that they're the same type of project and maybe they're using the same resources and you can only choose one or the other. So you can't do both of them. And what we saw earlier that was labeled Project 9 that was in this scenario, spending most of his capital in year 1 and 2, now has the option of either uh, starting in year 1 or starting in year 2. And there is a consequential erosion in the NPV if you start later by a little bit. But now you have the option of sort of either starting earlier or starting later, depending on what are your capital constraints. And you also have another project, number 7, where say, for example, maybe it's because it's in the same facility that this project number 7 is an option. And what I mean by that is it will only be a 1 if this project number 2 is a 1. And what I mean by that is it's not a must. So you can have a situation where you do project 2, but you choose not to do project 7 because you don't have the capital. But there's never a scenario where you do project 7 without doing project 2. So those are the different constraints. Hopefully that's clear enough. And we're going to try and reflect it in Solver. So again, just like before, we're going to use Solver. And here we're looking at similar constraints to before. So you're trying to maximize your returns. You're going to do that by changing column L, turning stuff on and off, essentially. Column L can only take 1, 0 values. But you now also have constraints where I've got two cells here, cell 19 and cell 20. I'm going to exit out of this one, just sort of explain why. I could have done it directly, but I was just doing it for convenience. Basically, I've added these two cells, and right now it's showing 0, and it's similar for this one. And it'll make sense in just a second. The reason why I did that is because if I've set it such that for, say, example, the light yellow cells, the combination of this and this has to be 1, which in a way forces the solver to say, I can only choose one or the other. So they're mutually exclusive. So that's how I achieve the mutual exclusive condition. I also have a scenario where L6 is L10, where basically the green cells have to equal to each other, meaning it's either both 0 or both 1. I have a cell L9 has to be less than cell L4, and that's reflective of the orange cells, where if you look at the direction of the inequality carefully, basically it's saying that uh, you can only have this if this is a 1, but it's not a must. So if this were 1, this cell L9 could be 1, but it could also be 0 because it's a less than or equal to. But definitely you cannot have it the other way around. You can't have this as 1 and this as 0. So by doing this, I've created a condition as well. And the rest of these are a bit more straightforward. It's just the individual capex for all the different years. So again, just like before, I hit solve. And takes a little bit longer now, but not really that much longer. And we have a solution. And that's using Excel Solver. Now, what I'm going to do now, which going to mark a change, is I'm going to step out of Excel. I'm going to start looking at doing this on Python. And we're going to be using a programming library, a library called PuLP. And PuLP is a linear programming library that works with Python, where it allows you to use Python to express a model. And I'm just going to walk you through. I'll post this up on a GitHub repo so you can walk through the code yourself. I'm going to run through it fairly quickly in this video. So basically, I've imported the information from a CSV file. And this information is exactly the same as what you saw a moment ago. This is just a check to make sure that I've got it right and it's coming in the right sort of data types. These are the capex constraints for year 1, 2, and 3. And now this is the part where we start getting into using PuLP. So the process is very similar to how you would do it in Excel as well. You create a model, and the way PuLP works, the syntax is that you've got to set a model and you've got to say whether it's a maximize or minimize type model. And then you build the variable that the decision variable that you're going to allow to change. So here I've called selection, and you can think of selection as column L, but in code. And I'm going to hit run. And then the objective function is basically the overall NPV for the selected projects. So if you look at the code, basically it's the selected project. So this is a list of this selection is a dictionary that contains an entry for every single project, and I'm multiplying it by the benefit value. So it's the same thing, but I'm just doing it in Python, and I'm going to add constraints. And this is the same process, except the expressing it looks a bit more daunting. But once you get used to it, trust me, it's fairly straightforward. So this is the constraint set, and the next bit is solving it. And there's a certain syntax that they use. We're just going to do that here. And you can see it only takes 1 second, and the answer we get is 72.75. It's exactly the same thing. You might be curious to see whether or not it's any faster or slower. And actually, to help with that, I've written a an Excel VBA that helps you do that. So we can actually do that right now, where if I just zeroize the cells, technically, because it's a linear problem, it doesn't matter what's in this cell, but I'm just going to clean that out. So I'm just going to run solver with timer. We're going to see how long it takes if you do it neck to neck. And you can see that 4 seconds in Excel and only 1 second in PuLP using Python. Now we're going to have to do a bit of a cleanup because the data is sitting in the background. So the rest of this code, I won't try and explain too much, but basically it's taking all the stuff from the PuLP model and spitting back out into a data frame so that it's easy to see. And this is the amount that is used for the capex phasing. You can see it's 2024, which is within the limit. So what I'm going to do now is I'm just going to grab the output for selection yes no. Selection yes no. Just do that here. And I'm going to just compare it to what is produced by in the solver model. So I know this is an ugly way of doing it, but probably also the fastest way. So let's just do it that way. We're just going to compare it. And you can see that it's almost identical. Actually, no, it is exactly identical. Doesn't have to be, but in this case it is. So we've arrived at the same solution and in a lot shorter duration-wise. Right now it's only 10 line items, but when you scale it up, these couple of seconds add up. And the benefit as well is here we're using a solver called CBC, where if you look at how Excel solver does it, you only offered a certain number of solver engines. And maybe I should explain what I mean by that. So the way solvers work, even with PuLP is a Python library that allows you to express your model in a Pythonic way. So you set up the model in Python, and inbuilt into PuLP, you're calling a solver, and these usually are very specialized pieces of algorithms that do very specific things of optimization. And with PuLP, you can actually swap out the solver, where if you want to use some other solver, you can type in solve some other solver name, and it will just use it. And there's a library of different solvers. This is missing in the plain vanilla Excel solver, but that's not really the main reason why writing it in code is better. The benefit you get by doing it in code is you actually get to separate the data part and the model logic part from each other, and you also get a lot more control in terms of versioning. What I mean by that is if you look at Excel, everything is all bundled together. It may be convenient, but it's actually a bad thing, because now if you send this file around, someone can mess with it, and you have the data that you can mess with, but you can also start messing with the solver settings. And if you start adding VBA, it gets a bit messy. Whereas with code, you can always store the data part separately from the model building part. And also you have much better tools for controlling script, things like Git, that helps you manage and track changes that you're making. So there is something to be said when models get a bit more complex, that you start going away from Excel and into a programming type approach. So this is the end for this video. Hopefully I'll see you in the next one. Bye bye.